The AI for predictive maintenance seminar series. I am Madhav Misra and I'm continuing hosting this seminar series. And Rise organizing this bi-weekly seminar with the exciting external speaker. So please feel free to spread this word to anyone who may be interested. And today we have a speaker, Dr. Nick Elfthrow. Sorry for your last name pronunciation. Yeah, sorry.
I'm used to it, so no worries at all.
So, this seminar from the Delphi University of Technology in the Netherlands, and he will be presenting on the topic of prognostics, the heart of predictive maintenance. Nick is assistant professor in the Faculty of Aerospace Engineering and specializing in sustainable AI for diagnostics, prognostics, and health management of the structure and engineering system. His research and developed innovative physics-informed AI models that improve the accuracy while reducing the AI's carbon emission. And of course, he's from the TU Delft. As said, the presentation will last approximately 30 to 45 minutes, followed by the question and answer sessions. As always, the seminar will be recorded and shared with the audience. So welcome, Nick. The floor is yours. Please start sharing your slides and share your thought then. Thanks.
Thank you very much, Madhav, for the introduction. Let me share my screen. Can you see my screen? Great.
Yes.
Great. Of course, I mean, I'm not still used to these web seminars, even if it has been like a long period that we are doing this kind of seminar. So if any of you is willing to keep his camera or her camera on, it's more than welcome. So it would be nice also to see some faces. So yes, as Matt have mentioned, I'm Nick Eleftheroglou. I am assistant professor in Delphi University of Technology in the Faculty of Aerospace Engineering. My research interests lie in the area of PHM, so prognostics and health management, in general for engineering systems, for engineering assets. And my main focus is in prognostics and diagnostics. So today we will discuss together about prognostics, the heart of predictive maintenance, as I call it. And let's start. So as you probably know, since also the title of the web seminars is about the maintenance, we have three main categories, three main strategies for maintenance. It's the reactive maintenance, the preventive maintenance, and the predictive maintenance. With the reactive maintenance, we allow assets to run to failure. With the preventive maintenance, we're preventing problems before they occur. And with the predictive maintenance, we are predicting failures. So, of course, each category has some advantages and disadvantages. For example, with the reactive maintenance, what we achieve via the reactive maintenance, the advantage is the maximum utilization of the asset. But we have many unplanned downtime period, potential future damages, and further damage to other assets as a domino effect of one damage, and of course, high maintenance cost. On the other hand, in addition, the preventive maintenance, we have less unplanned downtime, we have increased planned downtime, and we are also doing some maintenance of seemingly perfect assets. So we are wasting some remaining useful life of these assets. Last but not least, we have the predictive maintenance, since we are predicting failures, and the main advantage is that we have a holistic view of the asset health. And the main idea is to take the right decision at the right moment. Of course, there is some complexity into that kind of strategy. But our role also as academics, as engineers, it's somehow to reduce this complexity or even to make it easier for people to use these strategies, this predictive maintenance strategy, and implement it to real case studies, to the industry. So let's discuss a bit about the cost. If we discuss about the repair cost, of course, in the preventive maintenance, the repair cost is really low. And going into, let's say, the reactive maintenance, the repair cost is really high. On the other hand, the preventive cost totally different. So the preventive cost in terms of the preventive maintenance is really high, and in terms of the reactive maintenance is really low. So as you can understand, since we would like to take some decisions towards minimizing the cost, the optimum cost falls into the category of predictive maintenance. So in terms of cost, of course, the predictive maintenance is the right, let's say, decision, but also in terms of reliability. For me, okay, I know that it could be fun sometimes to don't really know what the future will bring, or to don't really know what's going to happen. But in my opinion, in such cases, that's not true. So we need to know. We have also the tools that we are able to make decisions about the future. And let's move on now to the predictive maintenance strategy, because based on all the aforementioned, we understood that this is the strategy that we have to follow for the maintenance planning. So with predictive maintenance, it's a maintenance strategy that uses data and machine learning algorithm to predict an asset when an asset will fail. So to predict the remaining useful life of an asset. So maintenance can be performed before the failure occurs. Of course, this strategy, it involves like collecting data from the assets and other sources, analyzing the data using machine learning algorithms, and use the results to make some maintenance decisions. So this strategy mainly consists of two processes, the training process and the testing process. In the training process, we gather all the available information that we have about this asset, some training data. We also have to choose how we will model the degradation process of this asset. And the outcome is to estimate some parameters. Then, going back to the testing process, we have our testing asset. We are extracting some data from this asset. We are doing some kind of feature extraction. We develop some monitoring data, some health indicators, and afterwards, using these health indicators and the estimated parameters, we are able to do some diagnosis. With the term diagnosis, I mean to predict the current damage state of the asset, and later on to move towards prognostics. And later on, having prognostics, we can go towards the decision making. So as you can understand, prognostics is the essential element of this predictive maintenance strategy, since it's the only element that provides the needed information about the future. It's the only element that can quantify the remaining useful life. Of course, diagnostics is an important parameter, since via diagnostics we are able to know the current damage state, but the only element that gives us an insight towards time, which is a really important parameter for a maintenance strategy, this information comes only via prognostics. So let's now talk a bit more about prognostics. Let's go back into history. I mean, at least the first step will not be really back into the history. And this is me. As you have understood, I'm Greek. I grew up in a place which is called Asplaspitia, which means in English like white houses. So this place is over here. It's really close to Athens, we can assume, let's say. So it was quite common every weekend or every second weekend to have some walks with my family, with my parents, and to visit other places close by. So one place which is really close to my hometown, it's Delphi. I don't know if you are familiar or if you know about this place, but in this place between the 7th and the 4th century BC, people from all over the known world would visit the temple of Apollo in Delphi to consult Pythia for personal matters. Pythia was the name of the high priest of the temple of Apollo. Pythia was widely credited for her prophecies, which are, let's say, under divine possession by Apollo. And her oracle powers appeared to be associated with vapors, probably ethylene gas. Let me show you. Yeah, this is Pythia, and this is the temple of Apollo. So as I was telling, her oracle powers appear to be associated with vapors, appear to be associated, in probably ethylene gas from the Kerna spring waters that float under the temple. So Pythia used these toxic substances, let's say, in order to give some predictions about the future. And be, let's say, the spoken person of Apollo and make this kind of prophecies. So as you can see, this place is really close to my hometown, so I really used to go over there quite often. And as a child, I was always really interested about how this was possible. How is it possible to make predictions about the future? How is it possible to know the future? So, and this is, let's say, my first way of learning and thinking about prognostics. But let's go now back into science. So in the next slides, I'm gonna discuss a bit more about the selected degradation model that I'm using in most of my case studies. And I will also define what the meaning of diagnostics and the meaning of prognostics. So in most of the case studies, I'm using Markov models. Markov model is a stochastic model that describes a sequence of possible events. So the main idea is Markov models in most are called state space models and can be characterized as clustering models. So the idea is like to define some damage states. In this illustration, we have 4 damage states. And the idea is to model the degradation process of this asset. And in order to model this degradation process, we can model it, let's say, via some sojourn times for each damage state. So to be able to know how many time units the asset will remain in one damage state, and also create some connections with the next damage states. The sojourn times can be geometric or exponential. It depends if we have a discrete domain or a continuous domain. But if we would like to extend that, we can use semi-Markov models. With semi-Markov models, we can model the sojourn time with any kind of distribution, parametric, non-parametric. We're also going to move into hidden semi-Markov models. Hidden Markov models, because the observations that we are extracting from this asset is not directly connected with the damage state. For example, imagine that we have an engineering system and we are extracting different kinds of data from this system, acceleration data, thermal data, any kind of data. Of course, this data includes some information about the damage state, but this information is not direct, that having these measurements, that means that we have this damage. So we need to model this connection, this hidden connection. And this hidden connection with hidden semi-Markov models can be modeled via these emission matrices, these beta parameters. And non-homogeneous, because we would like to include some extra aging parameters. So to be non-homogeneous in terms of time. The initialization process, as I already explained to you, consists of the number of hidden states, how many damage states that we will have, and of course the possible transition. Is it possible to transit from damage state 1 directly to damage state 3, or I have to pass from damage state 2 or go directly to failure? And the main idea, as I already explained you, we have two processes, the observation process and the degradation process, beta and gamma parameters. And the main idea is to estimate these theta parameters, these beta and gamma parameters, in order to characterize in the best way the condition monitoring data that we have. Then let's go towards the diagnostics. Diagnostics is the assessment of the current damage state, conditional to the available data and the trained parameters. So imagine that in real time, what we can see via the diagnostics, it's, let's say, if we have data till like for the first 60 hours, we can predict with this data the current damage state. And in this case, the current damage state, it's damage state 1. After few hours, like after 110 hours, this asset transits from the damage state 1 to damage state 2. So this is the information that we have via diagnostics. Now, in terms of prognostics, again, it's the same kind of story. We are using the available data in order to predict the remaining useful life. And of course, predicting the remaining useful life is a stochastic process, because as you can imagine, future and the degradation process of one asset cannot be deterministic. It's a stochastic process because it includes many kinds of uncertainties, like future loading conditions, other kinds of uncertainties that we don't know. So for me, it's crucial always when we are providing an estimation about the remaining useful life, this value to be a random variable. It's not possible to be a deterministic variable. So we can predict the mean value of this, of the remaining useful life, but also we need the confidence intervals. And let's also give like a definition, a mathematical one about the reliability. So what is the reliability? It's the probability that the asset will be alive at the time point t, conditional to the available data that I have till that moment, which is the time point tp, given the fact that my system hasn't failed yet, and given the estimated parameters that we have already, that we have calculated in the training process. So let's discuss a bit more about the prognostics. So what we can have as an output in terms of prognostics, let's assume that we start our experiment, we have our asset, and after 155 hours, using all the available data that we have and using the estimated parameters, we can predict the remaining useful life. And as I have already mentioned, the remaining useful life, it's a random variable, so we can predict the mean value. So this red line, it's the mean value of the remaining useful life, and also some confidence intervals. Here we have, let's say, the 95% confidence intervals. And later on, when the system will finally fail, and this asset fails after 220 hours, only at that moment, we will be able to plot the actual rule. And this line consists of 2 points. So what this line tells us, like after 220 hours, the remaining useful life of this asset is 0. And of course, at the 0 time point, the remaining useful life is 220 hours. But once again, this line is known only in the end. So we have used this kind of methodologies for many different kind of case studies, let's say for lithium polymer batteries, for unmanned area vehicles, also for aircraft brakes in collaboration with KLM. Also, I have used that for compressors. But now let's move towards one specific case study. And this case study, it's about prognostics of composites. As you probably know, high-performance composite materials like carbon fiber reinforced polymers are used in primary structures of aircrafts nowadays, like the Airbus A350 and like the Boeing, the Dreamliner. So, of course, many advantages regarding this kind of materials, like say that these materials are lightweighted. So composite materials can be lighter than traditional kind of materials. Also, they have high strength to weight ratios. They have really high durability. So they have, let's say, often highly resistance to corrosion and damage. Of course, we have a flexibility in terms of design and tailored properties to have, let's say, specific properties such as high, let's say, electrical conductivity and thermal resistance. But of course, there are some disadvantages. The heterogeneity that exists in composite materials, also the anisotropy, the interfacial effects of these two materials, and the complex manufacturing process make these materials a really complex engineering system. To be honest, based on my experience till now, composites for me is the most complex engineering system that I have faced. So I tried to do prognosis for composites, and how we did that, we just took some rectangular specimens, some composite rectangular specimens with this kind of dimension. And we had some loading conditions, like fatigue loading conditions. This is just a loading conditions that we applied. And we had, let's say, 8 specimens, 8 CFRP open hole specimens. These specimens are manufactured with exactly the same way, from the same material. The operational conditions were exactly the same, so same loading conditions. But still, if you observe the lifetime of these 8 specimens, we have a high variance. So specimen 1 failed after 22 hours, specimen 2 after 16 hours. And if we manage to identify the outliers of the training, I think it's specimen 4 that failed after 13.6 hours. And the other outlier is specimen 8 that failed after 30 hours. So we can see like a high variance in terms of lifetime. Of course, during the fatigue loading of these specimens, we extracted some axial strain degradation data. And over here, I'm presenting you these 8 degradation histories. So all these specimens started from the healthy state and they went till failure. So we have the whole degradation history. And the idea now is to use all the available degradation histories in order to predict the remaining useful life of the yellow one. I'm presenting you now the results of this specimen. Yes, we can say that the mean value of the remaining useful life is quite close to the actual rule. The confidence intervals, these are the 95% confidence intervals, include the remaining useful life. So someone could have assumed that, oh, this is great, it's such a great methodology, can provide really accurate predictions. But my question is, what is going to happen if we have some unexpected phenomena only during the testing process? So the training process has already happened. We have the data, we trained the model, but in our online system, in our online asset, we have some unexpected events. And for composite structures and in terms of aviation, imagine that this unexpected phenomenon can be some bird strikes, and we simulate that via online impacts with using a gas gun. So during the fatigue loading, we just took one gas gun and went directly to the composite specimen, and we had some impacts. Or we can also have some unexpected phenomena in terms of the manufacturing process. So to be honest, I didn't did that on purpose, but during the drilling process, the quality wasn't the same. So as you can see, the drilling process here has different quality than the training data. And then we did exactly the same feature extraction process. So we have these two new specimens, and these specimens includes now some unexpected event. And as we can see, the specimen with fatigue and impact failed after 10.5 hours. And the specimen with the manufacturing defect after 4.2 hours. So these are kind of outliers because our training process, the minimum lifetime that in the training process, the minimum lifetime that we have observed is it's just 13 hours. But our testing assets, but our testing systems have much lower lifetime. And over here, I'm presenting you the degradation histories of these two testing specimens. So let's use now the trained model that we have already in order to predict the remaining useful life of these two assets. As you can see, this is about the specimen with fatigue and impact. Now the mean values of the remaining useful life are not close at all with the actual rule, and not even the 95% confidence intervals. So this, we cannot say that this is a reliable outcome. And to be honest, and just observing the literature, it's quite uncommon people to present results and predictions of prognostics for outlier cases. So this is a really hot topic for me and a really important topic, since it's not possible to say that we have a reliable rule prediction model if we are not able to predict reliably and accurately the remaining useful life of outliers. And then going back to the manufacturing defect, the results here are even worse. So this is not acceptable at all in terms of reliability and accuracy. So here is the first challenge of prognostics, and the challenge, it's about data. But is it possible to have enough data for our training process that can characterize all the different kind of uncertainties that we are probably gonna face? So let's discuss a bit more about the sources of uncertainty. We have lifetime uncertainties, like past state uncertainties during the manufacturing process, like the drilling defect was a part of the past state. It's a part of a past state uncertainty. We also have present state uncertainties. Imagine that you are using some sensors in order to extract the data. The quality of these sensors is not always the same, because also the sensors are facing some fatigue. The quality, it's different during the lifetime. And of course, this is the main issue over here, it's the future state uncertainties. We don't know the loading conditions, or we don't know all the unexpected events that can happen in the future. And last but not least, we have user uncertainties. Since we have chosen a model to model the degradation process, and we have also some uncertainty in terms of our diagnostic and prognostic tools. But let's assume that we can have really extended experimental campaigns, that we can capture all the uncertainties, which, as you can understand, that's not possible at all. It's not possible to capture all the uncertainties that can happen in a real environment, in a real operational environment. But even if we manage to do that, then we have to discuss about the sustainability of AI. Because in order to train these models, just for the training process, we need some computational time. And of course, for the computational time, we need some electricity. And this electricity produces some CO2 emissions. So an example, and this is like extracted from a big language model. The carbon footprint of training a single big language model, it's equal to around 300 tons of CO2 emissions. And just to illustrate that, 300 tons of CO2 emissions is equal with 371 flights between Amsterdam and Athens. So my conclusion is, like, even if we are able to have really extended experimental campaigns to extract huge amounts of data, even the computational time of training models with this amount of data, it's not sustainable. It's not something that we can do. So let's talk now about how we can have a possible solution regarding that. So a possible solution, from my point of view, includes two steps. Either we can include some physics information in the training process and some adaptation steps in the testing process. With adaptation, I mean to use knowledge from diagnostics in order to re-estimate the estimated parameters and then use these re-estimated parameters in order to do some prognostics. From the physics point of view, for example, we know that in composite structures, we can observe three different damage states. Delamination, we start with matrix cracking, then we have some delamination, fiber breakage, and finally it's the failure. So in my case, that means that I can model and I can use for the hidden semi-Markov models 4 damage states, because that's the reality and that's the physics behind it. Also, we can include some physical meaning in terms of the predictions. So is it possible to the prediction of the remaining useful life at time point t to be higher than the remaining useful life at time point t minus 1? Also, are we expecting that the length of the confidence interval will be reduced towards the end of life since more data were available? So these are kind of physics that we can include, either in terms of the damage states or in terms of the predictions. So for the adaptation now part, as I have already told you, we can use the diagnostics. So here it's the prediction of the damage state. We can use this information in order to re-estimate the model parameters. With the constant lines, you can see the estimated sojourn times from the estimated sojourn time from the training process. And as you can see, the mean value is around, let's say, 25K of seconds, right? But using the diagnostics and knowing that the testing system stayed in the damage state 1 for 1.4 seconds, we can adapt these distributions in order to characterize better the testing system. So this is a part of adaptation. If you would like to know a bit more about this model, you can check the previous paper via the QR or the title. So now what I did, I even reduced 50% the training data. So I eliminate some degradation histories. These are with X. I used only the degradation histories from specimen 1, 2, 3, and 8 for the training process. And I tried now to do prognostics for the outlier cases, for the two specimens, the specimen of fatigue and impact and the specimen with the manufacturing defect. And these are the results. So this is the results of the classic model, and this is the result of the adaptive model. As you can see, in that case, we managed to have, in my opinion, really good predictions about the remaining useful life. The mean values of the remaining useful life is quite close to the actual rule. And this is for the specimen with fatigue and impact. And even for the specimen with a manufacturing defect, we were able to have really good rule estimations, even with the fact that, keep in mind that we reduced the available data. We reduced the training data half, 50%. But utilizing these two steps of adaptation and physics informed, we are able to have really accurate prediction for outlier cases. Let's move forward quickly to the second challenge. The second challenge, it's about the actual rule. Give an answer to yourself at that moment, which of these technique, which of these three different models, the first one is a Bayesian neural nets, the other one is a gradient boosted trees, and the last one is a non-homogeneous Hidden-Markov model, which model gives the best predictions? Let's think a bit. So, as we have already discussed, only in the end, only when our engineering asset has failed, we are able to sketch this actual remaining useful life line. But let's assume that this line has been sketched in case that our engineering system, the operational condition of our engineering system was perfect. So the operational conditions were the ideal ones. So in such a case, the remaining useful life could be 220 hours. But what if the operational conditions were a bit different? So after 50 hours, our asset faced some really harsh environmental kind of conditions. So that can probably mean that this line now could be different, the actual line. Or what if in the future, like after 50 hours, our asset, after 100 hours, our asset will be again in a really good kind of operational conditions. So as you can understand, the actual remaining useful life line is not always, it's not linear, it's not always the same, but the only, and it's a dynamic. So this linear line, it's a dynamic one, which and has been and this line will change at each time step. So ideally, let's say that our rule prediction should look like this, because initially the operational conditions were quite well. So the assumption that this asset will be alive for 220 hours will be a valid one. But afterwards, facing some other kind of conditions, the actual remaining useful life will change. And then changing again the conditions, the remaining useful life could be again differently, could be again a different one. So ideally, this will be the ideal predictions of the remaining useful life. So what I'm trying to say is that we are always comparing our methodologies with this line, but this line is not the actual rule. It's the actual rule that can be defined only in the end of the lifetime, in the end of the operation. But it's the only way that we have at that moment to compare different methodologies and to calculate the accuracy. So the second challenge is how we can compare different rule prediction methodologies, because it's not valid to compare these methodologies with the actual line that it's sketched only in the end of the life. So I'm also working now in that area, and we are trying to indirect calculate the accuracy and trying to find a way to somehow observe how dynamically this line will be changed. And this is a really important challenge in terms of prognostics, because this is a core question. We are comparing our rule predictions with something, but we don't really know this something. We only know the actual rule only towards in the end of life. So the only valid area to do comparisons is the end of life. But what about this area? So, and this is some conclusions. So let's move towards the conclusions. We discussed about the predictive maintenance. Why is the predictive maintenance important? We discussed about prognostics, the importance of prognostics. And then we faced the two main challenges of prognostics, which is the data challenge. Is it possible to have sufficient amount of data? My answer is no, but we can develop adaptable methodologies, adaptable in terms of the testing process, include physics in these prognostics, and in such a way we can even reduce the needed amount of data, and we can even reduce the needed computational time. And the last challenge, it's about the actual rule. The actual rule, that it's a challenge that we are facing now, and it's a really important challenge because we know the actual rule only in the end of life. So it's not reliable, it's not valid to compare our prognostic methodologies with this linear line in the beginning of the lifetime. Thank you very much.